Thank you very much, and thank you very much for inviting me to kind of give this. Yeah, so my kind of aim in the next hour, I suppose, is to give you an overview on many different levels of kind of what's going on in terms of planet formation. And necessarily, this is kind of focused a bit more towards rocky planets. And I'm an astronomer by background, so I'm probably will kind of come at things from more of an astronomy perspective. But I just wanted to kind of say now, everybody jump in if I use terms or something that's not clear along the way, because otherwise we're not going to get that. And I was also going to say I deliberately haven't specifically told the solar system story, because I think I could spend another 2-hour lecture doing that. So I tried to just kind of keep this generic today to rocky planets, which applies to the solar system and to exoplanetary systems. Cool. How do I move? Slide. Yeah, wakey. Yeah, so if we start out excuse me, with our own rocky planet, we know that formation was successful. We're all here living on Earth today. Somehow that planet managed to complete its formation, but during the building of our own planet, actually many of the things that happen probably are key to why our planet is like the way it is today. So the fact that we have plate tectonics, the fact that we have mountains, the fact that we have oceans, but we're not a water world swimming in it, are all kind of linked intrinsically into the formation of our planet. And the same must be true in kind of planetary systems around other stars. So I've just put up the kind of famous TRAPPIST system, just to kind of get us all in this vision of actually, when we see rocky planets around other worlds, they potentially share many similarities with our own rocky planets, kind of Earth, Mars, Venus, Mercury in the solar system, but actually maybe they're really, really different. And so the TRAPPIST planets, whilst being kind of Earth mass-ish, and one or two of them are Earth density, they're on very, very, very small orbits, very, very close to their star, which is now a low mass star. It's no longer a kind of sun star. This is a really low mass Earth M dwarf. And so the formation processes that lead to rocky planets have to do both form our solar system and these worlds like TRAPPIST and the many, many other planets that we kind of see. Okay, so the big question, how do rocky planets form? And so first of all, let's just think why we want to kind of know that. So when we're forming rocky planets, actually, those formation processes are going to determine the size or the mass of those planets. And that's going to be really important for what kind of those planets are like on their surface, what's going to kind of carry on. It's going to determine what those planets are made from. And that can be both on that kind of broad level of, are they ice giants, gas giants, or rocky planets, but also on a detailed level of what's the magnesium to silicon ratio of the rocks that go into this planet based on the exact kind of history of that planetary system. And that in turn will just determine some of those geological processes that are going to be occurring on those rocky worlds. And eventually, therefore, what it's like on the surface. Do we have land at all? Do we have mountains? Like maybe as we're kind of thinking about life here, like how does that planet formation process determine whether or not life could originate on these rocky worlds? So hopefully in the next hour, I'm kind of going to go through these kind of, what I put, 5 key parts of planet formation. So we're going to start really, really early, thinking about star formation and how we get a planetary system at all out of those big molecular clouds. Then we're going to think about the first stages, building those planetary building blocks. And I'm going to use the term planetesimal, but that could be asteroid, comet, building block, they're all kind of interchangeable. And that's really the first stage of forming planets, these kind of kilometer-sized rocky things. And then we're going to talk about how we can form gas giants, because that's a necessary kind of precursor to rocky planet formation. And talk about the potential kind of controversy between this loss of envelopes in gas giants leading to super Earths potentially, and how that relates then to kind of late stage rocky planet formation as we kind of think of it maybe more traditionally in the solar system as this kind of collisional process with giant impacts that led to the moon, say, and then that formed planets kind of like Earth after the gas disk is gone. So let's start off with our stars. And so I kind of always love these beautiful pictures of kind of star forming nebulas because they always look amazing. And so we kind of, if we take ourselves, these are really the birth places of where planets are going to come from. And I kind of like to think of actually everything is there that you need to form your planets, but nothing's started yet. So this is like the ingredients for cooking your cake. You put out all the amounts of sugar and eggs and whatever lovely fruit you want to put in your fruit cake or whatever on the side. but you have not yet formed it. But what you put out there could be different, and we already know that star forming regions earlier in the universe were much more metal poor and had different abundances of all the fundamental elements that we need to form a planet. So already that star forming cloud is going to tell you what kind of planets that you can form. And I think I wrote that down on the next slide. And I kind of wanted, from a solar system perspective in particular, to think about these kind of things like short-lived radioactive nuclides and long-lived radioactive nuclides, which are the things that potentially led to large-scale melting asteroids in our solar system. Actually, whether or not you have those within those star-forming clouds depends on how close you were to other massive stars that potentially produce those species. And so some systems probably have them and some probably don't. Yes, I don't know whether to put this slide in, but because it's very complex, but actually it kind of nicely, I think, shows the next stage. So don't worry about reading all the text, where we've kind of started with our molecular cloud. That was this massive cloud of gas, and we've collapsed down now. Some part of it became gravitationally unstable, started to collapse down to form our star. We start forming the star in the center, kind of here, of what becomes this kind of planet-forming disk. But this process has to remove all this angular momentum, so potentially you end up with these jets of material leading out of this planetary system within kind of this. And potentially in that star-forming region, you would have had many, many of these planet-forming disks kind of forming. Yeah. And then I'm sure that some of you have seen this picture before. This amazing kind of ALMA has totally revolutionized our idea of these planet-forming disks. Producing all these beautiful, beautiful images. This is HL Tau, which is a very kind of typical system. And what's really, really special here is kind of pre-ALMA, we had this idea of these kind of we call them class 2 systems, where you collapse to form these kind of very flat disks now, which is where you're going to form your planetary bodies. And with ALMA, we started to see the structures inside of these disks. So yeah, the resolution here is not great, but you can start to see that there are rings there. Within this disks, and potentially these are related already to the formation of big bodies or even planets. And actually we even have ALMA observations of kind of young gas giant planets forming in the outer regions of these really, really young planetary systems. Yeah. And so that kind of leads to an open question, and this talk can be full of open questions because planet formation is full of open questions. And that is, when did planet formation start? When do you form those first planetary building blocks? And so this slide, I think, kind of indicates or kind of demonstrates part of the mystery of whether those first planetary building blocks really were starting to form already when you've got your star formation going on and you're just collapsing, or whether they're forming later when you have this kind of fully fledged protoplanetary disks, or even in debris disks. So this plot is showing the fraction of stars that have a mass above whatever's plotted here in dust. And it's showing this because this is something that we can observe. So we can look at these different kinds of disks and we can say how much mass do they have in millimeter-sized dust, probably with ALMA, and we can kind of convert that to a total mass potentially. And what you're seeing here is that in the youngest systems, so these class 0 systems, they're really like the start of star formation still is going on. The same with the class 1, you have a lot of systems with a lot of mass and dust, but that over time that dust is disappearing until you get down here to these kind of, you can hardly even see on here, these faint orange ones, debris disks, where actually that dust is totally gone and you're very, very dust poor. And that dust presumably was the stuff that is going to form our planets. And so these kind of ideas are showing us that maybe planet formation actually started really, really quite early. And we're converting that dust into planets early on in those planetary systems. But I think that's still very much an open question in the field as to when that happens and how it works. Okay, so I'm going to move on to a cartoon now, which actually comes from an outreach talk I gave years ago, but hopefully you'll appreciate the pictures that go with it in a second. So it's just starting with this kind of idea of how do we go from those dust particles into our planets. And so the cartoon is kind of showing this planet forming disk, and the cartoon shows it as having collapsed, but maybe it's still actually puffed up and star forming. But in the center of this, basically you have lots and lots of gas and you have tiny micrometer-sized dust particles. And those micrometer-sized dust particles are the things that are going to become planets. but they've got to do a lot of growing, right, to get from micrometer-sized dust particles to Earth. But the first part is actually pretty easy. And so what happens is those kind of small dust particles, they start to collide together, and the velocities at which they're colliding inside of that kind of gas are very slow, and that means that you end up with these kind of gentle, slow, sticking collisions. So they gently make these kind of big fractal dusty aggregates, which grow then maybe from kind of, we said this is a joke, it's like the babies kind of growing from these micrometer-sized things into basically millimeters or centimeter-sized particles, which are kind of like your toddlers. And this kind of growth we can look at in the lab. So people have done these lovely experiments where they show how these, in zero gravity, how you can get dust particles to collide at the relevant velocities and how they stick together, form larger things, and actually grow into these kind of very porous, fractile, fluffy dust grains in the early stages of planet formation. So that's all great, but we want to keep going, right? We don't want to be stuck with millimeter-sized dust, because that's not going to help us form a planet. And that's where we start to run into problems, because ideally we would just have our millimeter-sized dust and it would grow into centimeter-sized things and then meter-sized things, and then suddenly you've got kilometer-sized planetesimals. But unfortunately, that lovely picture really just doesn't work. And we can't grow meter-sized things just from this kind of commutative accretion. And there are various reasons why not. One of them is that once you become big enough and you do that kind of nice collisional growth, then those kind of nice collisions that I was talking about, where these dust particles come together and stick, actually when you're large, the velocities start to get higher because of excitation, and then they become what are known as bouncing collisions. So they no longer stick, they bounce off each other. And so this was kind of rather sweetly termed the bouncing barrier. So it's very hard to get growth beyond a certain size from these gentle collisions, just because you hit what's known as a bouncing barrier where things no longer stick. There's also a fragmentation barrier. So once you get even larger, you can, when you hit against each other, you don't even bounce, actually you destroy and you become smaller again. And so those collisions no longer getting you bigger. And then crucially, within these systems, there's something called a radial drift. And so you end up with this radial drift barrier. So if you can imagine, this is kind of your star, you're in the midplane of your disk, and things are growing, they're getting larger and larger, but actually you've got gas all around you. And that gas is orbiting at slightly sub-Keplerian velocities. So this dust that's now inside of that gas is constantly feeling this headwind. So as the dust tries to move, the sub-Keplerian gas, it's moving at Keplerian speeds, then it feels this headwind, which causes it to slow down and to spiral, the orbits spiral inwards. And you can kind of quite simply analytically work out the rates at which that happens. And when you grow from millimeters to bigger things, you hit what's kind of known as the meter-sized barrier, which is basically when your time for growth is much shorter than your time to end up on the star. So if you were to like allow this disk to do nothing but this kind of gentle sticking, things would get up to meter-sized, but then everything would be hit. And so you would never grow bigger. And so this is kind of the radial drift barrier is a really important problem in planet formation. And so how do we overcome that? We want to form these planetesimals, these big kilometer-sized things. Well, we kind of have to skip it and jump straight to tens of kilometers. I think I put, the cartoons. I kind of see it like we were having our babies and our toddlers, and then we said we wanted to become a child, but actually we never made it. We just skipped childhood entirely and went straight to being a teenager, which is a bit of a shame, I think. And so what happens is in these kind of dense gaseous environments, so these are kind of showing simulations of the inside of these planet-forming disks, just showing physical space. If you start increasing the densities that you have within that, such that you have lots and lots of dust, eventually you hit this instability that's known as the streaming instability, which leads to local gravitational collapse. And those local gravitational collapses end up forming locally then enough dust, which you then form a kilometer-sized planetesimal. So you go straight from your kind of millimeter or centimeter-sized dust particles straight into your kilometer-sized planetesimals. But really, really importantly, the streaming instability only works when you have local enhancements of your gas to dust ratio. So this has to happen at some point in the disk when either evolution has been such that you've got enough dust around, or you've got some kind of trap, which people often refer to these kind of pressure maximums outside, say, of Jupiter's orbit as being a good place. Okay, so we've got planetesimals forming from these streaming instabilities, but we still want to get these rocky planets. So how do we go from these kilometer-sized planetesimals all the way to planets? And first of all, let's think of this already in the early stages of the gas disk. So there's loads and loads of gas around. You've already quickly formed some of these planetesimals. Or actually, if you grow fast enough, then you don't form a rocky planet at all, you form a gas giant. And a kind of important thing here is that gas giants are only going to form if you can accrete enough solids that you form a big enough core that you can then get runaway gas accretion. So you have lots and lots of gas around in that disk that you need to have a big enough core to then take on all of that gas. And so what is actually an open question, I think, in the field, although I'll argue a bit both in certain direction in a second, is whether or not those cores form predominantly from what's known as pebble accretion, or whether actually they form from having formed these planetesimals and then accreting many, many more of these planetesimals in a kind of collisional way. And so probably a bit of both of these processes happen. So the pebble accretion scenario is where inside of that gas disk, actually we talked about how we have this kind of radial drift of bigger things. So you form very easily micrometer sized to kind of up to millimeter to centimeter sized things. And so those bodies grow very easily, and therefore you have this wonderful open supply of what are known as pebbles, basically small centimeter sized rocks, not nice and spherical properly like these, but probably more like fluffy, dusty aggregates, are all over your disk. And actually, therefore, it was kind of the idea came about that you could grow your planetary cores just by accreting those pebbles rather than having to form lots and lots of planetesimals. On the other hand, the kind of more traditional model is where you have these big collisions where you formed lots of planetesimals, which then the planetesimals merge together through collisions and then eventually grow to form your kind of multiple Earth mass core that you need for a gas giant. But the problem with planetesimal accretion is firstly, you need the conditions that you need in order to have streaming instabilities, but then also for the planetesimal accretion growth to be sufficiently efficient, you really need like very high densities of dusty material inside of your disk. And once you start having multiple planetesimals, they start exciting each other and those collisions stop being accretional instead. So it's very hard to get very efficient accretion enough that you can form the core of a gas giant before the gas dissipates. So you have to do it early enough. We know Jupiter and Saturn exist. But that being said, the planetesimal accretion is absolutely going to be important in the late stages, potentially of those cores, or in fact in rocky planet formation. Yeah, okay. So back to kind of pebble accretion. So as I said, the disk is now full of all these kind of pebbles, just because those are the things that most efficiently grow, and they're very efficiently accreted. So once you've had some planetesimal formation, maybe in the streaming instability, those planetesimals can very efficiently accrete all of those pebbles and grow. So this is some plots from the original, from a nice paper from Johansson and Lambrechts in 2017, show as a function of where you are in the disk, the mass of various things which are growing via pebble accretion. So basically what's happening is you start with something kind of, you have to start with something that's already grown big enough that then you can accrete enough pebbles. You actually grow relatively rapidly. So the time is here in 0.2 million years, up to here, up to a mass large enough that then you have runaway gas accretion. So that's when you become your kind of Jupiter mass planet up here. So once you become above that, a certain kind of critical mass, then you grow rapidly to become a gas giant. What's kind of nice about pebbles is that we're starting to find evidence from comets that actually a lot of the material within the comets actually is pebbles rather than having been from kind of multiple planetesimals. And so Rosetta has been absolutely amazing in doing this. So there's a lot of text on here, but I wanted to kind of put all of the different things, and you can't see this figure. Yeah, okay, so this is from the Rosetta mission, and basically the thing to take away is that there were various different ways in which you can kind of measure the size bodies that were inside of the comet 67P. and to work out what kind of size things are dominating the mass. And some of these come from measuring the temperatures at the surface. Some of them come from measuring how it responds to heating, these two here, and some of them come from measuring the dust that was actually released and the size distribution of that dust, as well as its strength. And all of these are they're consistent with a whole range of different size things, but actually if you put pebbles being at kind of maybe a centimetre or so, here in the middle, this plot is kind of showing you that actually pebbles could explain a lot of the observations from Rosetta. And so I think that's really cool that this kind of comet, which is essentially a large planetesimal, looks like a lot of its mass came from pebbles rather than planetesimal accretion. Yeah, do jump in if I'm going too fast or anything's not clear. Cool. So then I just wanted to kind of show this about, well, within our solar system, if we want to get rocky planets, we first have to form the gas giants. And so this plot is kind of showing how we can do this. So this is as a function of time, looking to the gas disk being available in the planetary system up until here, and then disappearing. You can imagine that you had your planetary core now, which forms large enough that it grows potentially from planetesimals, potentially from pebbles, up until a mass when runaway gas accretion takes over. So up until here, you're mainly growing solids. Then suddenly you have runaway gas accretion and you can form your gas giant up here. But what I don't like about this figure is they seem to be the same line, but if you do accrete it just slightly slower on this bottom line here, then the disk can disperse before you get to the threshold for runaway gas accretion, in which case you form something that's much more like, so it contracts when it cools and you form something that's more like the ice giants, so Uranus and Neptune in the solar system. So kind of the point I wanted to take from here is timing is key to everything in this kind of stochastic manner in exoplanetary systems. If we want to form different things, it's how much growth do we have compared to other timescales like the gas going away. So it kind of gives us these different outcomes. Yeah, and then I kind of thought from exoplanets, now we have this kind of idea of the loss of envelopes of these planets and how potentially these could explain some of the observations. So for kind of exoplanet astronomers, this is a plot that goes up everywhere and everyone loves, but for the rest of you, this is showing from kind of the observed population of planets that we have, the number of it's basically the number of planets as a function of their size. And what you see is that there are these two populations, and there are multiple ways you can explain this. You can kind of say there's a difference in composition between these, and we often call it the mass radius value. But one potential way of explaining it, it relates to the loss of envelopes of these gas giants. So just to confuse you all, I've now taken that plot and switched it on its head sideways, but it is the same plot. So if you're awake, this is the number of planets per star, and this is now planetary radius, and there's two bumps here. And so these are the sub-Neptunes here, which are these kind of things that we think have these big H2 rich atmospheres. And then down here, we have lots of these kind of more rocky planets potentially without atmospheres. And one way to explain this is that you kind of formed, as I was showing from that cartoon, you form lots of things that have these big, thick primary atmospheres. And then you have some process, potentially photoevaporation, potentially core powered mass loss, which leads to the removal of these thick hydrogen atmospheres, leaving behind the kind of rocky planets or planets with very thin atmospheres that then can explain this kind of second bump of kind of rocky planets in this mass radius distribution. Yeah, and I think a fascinating question, but it's very much an open question still, is like when we see a super Earth or we see a rocky planet like this, did it form in this way from something which had initially had that kind of gas giant formation mechanism where it created a big envelope and then lost it? Or did it form in a kind of more traditional rocky planet way to form something that was just purely rocky after the gas disk was gone? Yeah, so then I'm gonna kind of talk about what we more traditionally think of as rocky planet formation, which is these kind of ideas of things going on after the end of the gas disk related to collisions. So did you have a question, Martin? No, okay. Yeah, so in my cartoon diagram, if we kind of go back, we managed to get from kind of micrometer-sized dust to centimeter-sized dust. We then skipped growing to anything bigger by directly forming these planetesimals collapsing out of the disk. And we now want to form these rocky planets from those planetesimals. So that's the kind of part of the process we're on now. And so in the traditional kind of thing, you can't see anything of my slides. Oh, there we go. The traditional kind of late stages of rocky planet formation were dominated by these collisions and these big impacts. And I'm pretty sure that giant impacts did happen really, really late on. But there's, I think, still a very big open question as to how much of that rocky planet formation, how big did you get before you started kind of being dominated by these rocky impacts? And people have even postulated that maybe pebble accretion is really important here. What did I look next? Yeah, so I just kind of thought I'd show you how this would work. So this is a kind of simulation of thinking where you say, okay, we have a load of planetary embryos. Those are kind of planetesimals, or in this case, slightly bigger than planetesimals, kind of 1,000 kilometers type things, and they're all colliding together. There's no gas here anymore. And this is showing a semi-major axis, and then the eccentricity or the inclination of all these little particles. And every time they collide together, sometimes the velocities are high enough that it's slightly destructive, but for most of the time, those velocities are low and gentle, and so the things collide and stick and grow until you kind of get to this point where you have what's known as oligarchic growth. So you have this runaway growth over here where everything was colliding and growing, and then one of these guys gets to be bigger than all of the others, and he says, no, 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 none of the rest of you are going, and he eats everything up, and it's the zone around it. So these are the kind of oligarchs that then can go on to form, say, Earth in our solar system, or yeah, so these are kind of, the simulation finishes at maybe Mars-sized things, but they can then accrete everything around them in that kind of very collisional way and become the terrestrial planets that we have in our solar system. And crucially, we know we have direct evidence, at least within the Earth, that we had some kind of giant impact very late in our history, because we all know that we have a moon, and that moon is a substantial fraction of the mass of Earth. Exactly what happened during that collision, people often nickname the impact a Thea, but that was a collision that was at least with comparable, if not equal-sized bodies that happens very, very late in those late stages, and leads to the formation of the Earth and the Moon system. And I think something else that we have evidence of from Earth, which is really interesting, is that even after that moon forming event, that those kind of processes of planet formation continued. And so in the simulation, we saw there was a lot of stuff kind of hanging around and flying everywhere. Most of that is gone by the time you form your oligarchs and they grow to become planets, but some of that material does remain and can be accreted by planets kind of after you've formed an iron core, after you've had your moon forming event, or kind of fully formed, and that's known as the late veneer. And at least for Earth, we have some observational evidence for exactly how much material was accreted during those very, very late stages. And that observational evidence comes from this plot down here, and I'm really struggling with my Zoom windows today. They're always hiding everything. And so this plot is as a function of the condensation temperature, which is basically telling you how refractory your elements are. So these are all different elements. It's telling you how much in Earth we have of all these different species relative to CI chondrites. And I always like to think of it as astronomer relative to the initial composition of your disk. And basically, I wasn't going to explain all of this, but what we want to take away is that there are some elements that should have gone to the core, and those elements, we still see them in the mantle, and they're the highly cytophile elements down here, and those ones probably were delivered during the late veneer. And they give us an idea of how much of that kind of very, very late stage accretion happened for Earth. Yeah, so hopefully you kind of got the impression as I was going through about planet formation that actually we don't know everything by a long way, and there are many, many open questions. So I kind of wanted to talk a bit more in detail about some of those now. And I think one of the biggest open questions kind of for rocky planet formation is this idea of pebble versus planetesimal accretion. And it applies for gas giant cores as well as it does for the late planets. So we talked about pebbles being these kind of small things that are available in the gas disk, but actually Earth or kind of proto-Earth could have formed to quite a large size already during that gas disk, potentially from the accretion of those pebbles. Could also have grown to quite a large size during the gas disk from the accretion of planetesimals, which then could be followed by this late stage of planetesimal accretion post-gas disk. And I think that's very much an open question that's being debated a lot in the literature, is how much does pebble accretion contribute to the formation of gas giant cores, and how much does it contribute therefore also to the formation of terrestrial planets? And probably the answer is it's a bit of both, but it's a question of mass budgets. I think also a very, very interesting question is regarding rocky planets specifically, is how big do those rocky planets get before the gas disk goes? So in that kind of scenario of super Earth formation, where they lost their hydrogen-rich envelopes, those super Earths actually fully formed during the gas disk. And in fact, they got even bigger because they were able to accrete those big envelopes, which they then lost, and you ended up with a rocky planet. So that's kind of one extreme end member, I suppose, of showing that rocky planet formation was very highly progressed during that gas disk. The other kind of extreme is that actually you didn't even get further than planetesimal formation for Earth during the gas disk phase, and you just had purely collisional evolution that formed Earth when there was no gas around later on. And probably we sit somewhere in between those two, but I think exactly where on that balance Earth formation sits is no longer is an open question, I would say. As is kind of this idea of giant impacts and those really big collisions that happen in the late stages of rocket planets. They're clearly incredibly important for what kind of planet you form, whether or not you had moons, how much you disrupt the geology whilst it's forming. But actually, we don't even really know in our solar system how many giant impacts even Earth had in its late stages. I think for Earth, we can say the answer is at least one, but did Venus suffer giant impacts late on or not? I don't know. And for exoplanets, I think it's even more of an open question. So we have observations from infrared observations of disks, where we see very, very dusty systems that are very young. And we think, well, maybe that's terrestrial planet formation in process, and you're seeing the kind of aftermath of giant impacts. But how often and what's going on there, and whether that really is representative of what happened in our own solar system's history is not clear. And then I also think, crucially, if we want to think about kind of life on Earth and we want to think about the composition of our planet, actually, that really late stage accretion that happens once the planet's almost fully formed and that gives you that late veneer, that's really important because that has the potential to deliver different kinds of computational material and leave it in your planetary mantle than you would otherwise. And it also has the potential to deliver stuff from further out in the disk that would have otherwise not got in so close. Cool, so I steamed ahead as always. So I just thought I'd kind of have this cartoon to kind of summarize almost everything I've said, hopefully in one fell swoop. So it's kind of showing the idea of planet formation starting with in these big molecular clouds where we're forming our stars, where we're already going to collapse down into those kind of proto-planet forming disks within that star forming region. And inside of those planet forming disks that we have grains, and those grains can readily grow from micrometer sized things to maybe centimeter sized things, so those pebbles that dominate your disks, but that we have this meter sized barrier where we can't get that kind of nice collisional growth is now stopped. And therefore, if we want to get planetesimals, we have to do something to kind of jump over that barrier. And so we go straight to those kilometer sized planetesimals directly in this instability known as the streaming instability. And then we kind of have this idea that within the gas disk, if we keep accreting pebbles or planetesimals onto those planetesimals once formed, we can form the cores of those gas giant planets. And if they form large enough, early enough, when there's enough gas around, you get runaway gas accretion, which leads to Jupiter, say, or Saturn. But potentially, if you're in an environment where there's a lot of radiation field, for example, very close to these stars, you can have the photoevaporative loss of those envelopes, and then so your gas giant that formed actually ends up potentially as a super Earth, having lost its envelope. And then kind of concurrently to this, you can have the growth of bodies early on from those planetesimals, but then your gas disk dissipates and is gone, and you're left behind with these rocky things which can grow via collisions, potentially violent collisions in those later regions of giant impacts, and it's those collision or accretion that then leads to kind of rocky planets like Earth. Yeah, so I'm going to finish there. I'm very welcome to take questions, and we've got loads of time.
Thanks very much, Amy. Questions?
Yeah, in terms of envelope loss from some gas giants, I'm trying to super Earths, what mechanisms would that happen?
Yeah, so this again is a kind of debated field. I'll try not to show my biases. So that one of them is photoevaporative mass loss, which is basically the UV radiations in the star can give you enough energy to lose them. An alternative to that is what's known as core-powered mass loss. And I think there's debate as to whether the mechanism even works, but it's basically the internal heat energy being released being enough to kind of allow that drift off. Yeah.
So it's clearly a very multi-stage process, and I only claim to have very basic knowledge about maybe one or two of those. But what strikes me about all of them is that they've all got their inherent kind of problems, difficulties. We had a journal club this morning looking at the stream instability. We don't even know the physical mechanism like underpinning it. And so therefore, do you think it is possible to get a overarching picture of how this all fits together? And if so, maybe what is the most pressing part of this picture that you think we need to target our attention at?
Oh, these are very tough questions. I think there's this like dream, right, that you can do the amazing simulation that resolves everything from your star right down, including your dust, and then forming your planets. But as you say, you never can. And so you always have to start with something and say this works in this regime, right? Yeah, I think what people are really excited about at the moment is probably kind of this bit between here and like how do you go from streaming instabilities, if it is streaming instabilities that form our planetesimals, to terrestrial planets, and how much of that comes from pebble accretion versus how much of that comes from kind of rocky planetesimal collisions within a disk, and how we can link that with maybe solar system observations as being our best clue as to what's going on there.
Cheers. I was wondering if the gravitational instability.
Yeah, sorry, I skipped that entirely. But it's also potentially important. It's probably, I think, unlikely to form rocky planets, but maybe somebody can tell me that they disagree with me on that. But in those early stages, probably I should add on another thing up here of star formation in your disk. If you have very massive disks, then in the outer regions of that, that's how you can kind of have from GI and collapse to form gas giants, or even bigger than gas giants, essentially brown dwarfs.
One of the things that really interests me is by skipping the kind of small planetesimal stage through the streaming instability, and what the implications are of taking a lot of small particles that can't, they've got no significant internal heat, so they're small and cold, and then instantaneously making like a very large object, multi-kilometer sized object from them. So you're kind of short-circuiting what would otherwise be slow growth, maybe slow heating, both collisional energy and internal energy, which could drive off volatiles and blah, 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 go straight to something which is large, and then make, kind of differentiate straight away. And what's the chemical consequences of those, the classical kind of planetesimal type accretionary view versus the streaming instability followed by pebble accretion, where essentially every step of that growth is a small thing.
Yeah, I think even more interesting actually is that later stage pebble accretion for that, because you can already have your planetesimal that, as you say, is differentiating, is losing heat, but instead of like gaining another big body, actually it's just gaining really small stuff. So yeah, I think there's kind of questions of like, how does that work for your radio structure, and do you redistribute it afterwards?
Yeah.
Oh, great.
They use animal observation where you can actually see the orbits, or at least of large planets that are forming.
Could you calculate, like predict their orbits in the future, see that some are they're unstable and you're going to end up with some kind of giant impact eventually?
Yeah, I was going to say, see the orbits. So the ALMA observations,
Sort of.
the ALMA observations show you gaps in
Yeah.
disks, which may or may not be planets. Right, so one possibility is those gaps are carved out by planets, but there are plenty of papers showing how you can produce those gaps purely through disk physics. And I think the jury's still out in terms of like actual orbits of planets. Like there are one or two that have young planets now discovered in disks, but that's one planet. And getting the orbital trajectories of that kind of planet when you're on a 100 AU orbit and we've got human timescales, we're just not going to we're not going to get enough of the arc to know really what it's doing.
And I guess the orbit's also going to be damped by the presence of the disk, right? It's going to be, the disk is participating in the orbital evolution of that in a way that's not a kind of clean n-body scenario of point masses.
We can't even do it properly for asteroids.
Yeah.
So like, we stand no chance like predicting whether asteroids are going to collide.
Sorry, what are the other like what else could gaps in disk be caused by?
That's a very, very good question. Where are my disk people? I think you can do some things to do with growth and changing your opacity, but I'm not expert geology.
Yeah, I guess anything that changes the dust properties or abundance locally. So if you did just have some growth from somewhere, you have very different sized particles, they just have very different optical properties. If they have, you can end up with places that you get a lot of ice deposition, which will also just grow grains, make them bigger. So that's definitely been one suggestion, that it could just be bumps near the snow lines where things are freezing out. But I don't think there's much evidence that at least those locations match the expected temperature profiles, for example. There's also magneto-hydrodynamic instabilities, which give you kind of radial pressure variations naturally, but I don't know anymore.
There's also a bunch where if you've only got one planet as well, one planet can like launch waves which can non-linearly shock and cause like multiple rings too. Yeah. So you might be deducing about 5 planets and there's only actually one which is doing it as well. So.
Is it the AS209? Is it that one that there was a paper that was, I can't remember who was first off, but just Richard Booth.
I know they're
showing that there's 3 or 4 rings, but they could all be consistent.
Yeah, I just know that I think the theoretical and numerical simulations that were done on this about non-linear shocking, but yeah.
Thank you, guys.
What determines the timescale for the gas dispersal? And if it's tied to stellar evolution, then can you predict like how dwarf planet populations would be different with like a pre-main sequence evolution?
Yes, definitely there is. So I think we don't know exactly how long gas disks last for from a theoretical point of view. We can, so photoevaporation is a good way to kind of finish that process. And there definitely observationally there are trends with stellar mass for how many objects you seem to have at what ages. So potentially you can make predictions for it being easier to form different populations, but then you have to take into account that if you were, even if your gas disk is longer, if you started with initially lower masses in them, because they went with lower stars, then your growth is going to be less efficient, so you might not necessarily get further per unit time. There's some interesting work recently that's kind of re-evaluated those traditional plots of how long the gas disk lifetime was based on several star forming regions, re-evaluating their ages and suggesting actually rather than kind of that 2 million years, that maybe some of them last maybe as long as 10 million years, which really I think changes this pictures in ways that people haven't really worked out yet.
Yeah, I thought it was pretty cool with the HSEs and kind of the sinking time scales and that about the kind of late delivery of material. I don't know really much about that. What are the time scales associated with this kind of partitioning, settling and sinking?
So I think it's more that if you've already formed your core and you've had that process of kind of metals segregation early on, that those things should have been in the core,
Mhm.
but actually we see them in the mantle, and so they shouldn't be there at all. So
But if they deliver to the mantle, will they stay there, or will they settle over some time scale again, a bit like in white dwarfs, if you've got a delivery of material and then they'll sink and drain away?
No,
do
I
you
think
get
they'll
that
stay
on
there.
Earth as well?
They won't end up at the core.
it won't down the core because
Okay.
there's no iron to take it. So it's when you form those iron droplets, you put the things that go with the iron in there as well. So I think the
So they're
highly,
still there now, right?
yeah, they're going to be there forever.
Okay.
So
You need some physical mechanism to drain.
Okay.
If
So it's
there's
not
no
like
iron
a-
liquid, if there's no iron liquid left to drain, then they'll just stick around.
In terms of the ages, like the formation age of the Martian core is estimated to be less than 10 million years after like birth of the solar system, possibly actually a lot less than 10 million years, so very early core formation. Earth's core formation is dated, or at least the last epoch of metal silicate equilibration on Earth is dated rather later, like of order like 100 mega year. And that may be due to the moon forming impact, kind of reopening the system to metal silicate exchange later on in the planet's life. Whereas Mars, was born, segregated its iron core, done, closed, and then a bit of late addition of material in the same way.
do we have any idea about the late addition of material from Mars?
Yeah,
Measure how much?
it had less late accreting material than Earth, but still some. Well, that's the inference anyway.
There might be a question in the chat.
Oh, yes.
Okay, Helen Williams says, great talk, Amy. Something I've always been confused about is how to quantify the contribution and importance of pebble accretion versus stochastic accretion to rocky terrestrial planets. I think that's a very good question, Helen, and I would love to know the answer. Yeah, so Johan Anderson had a paper recently, Anders Johansson had a paper recently trying to look at pebble accretion for Earth and postulating that actually maybe you could do it entirely with pebbles. And I think it works for some things, but I don't think it works for all of the geological constraints on abundances for Earth. And so I think there are kind of potential kind of ways to get access to this problem, but actually it's still very, very much an open question. Does that help, Helen? It's probably not even there anymore.
Do you know what it fails to do? What, as an example, is it's not purple?
Oh,
If I had to guess, I mean, I don't know the answer, but if I had to guess, like the work that we did with like John on the manganese sodium, and so Earth is volatile depleted.
Yeah.
And I think the question would be, like, you could have inner solar system pebbles that are volatile depleted because they condense from a hot nebula. So you could maybe explain it that way, but there is a fingerprint of volatile depletion, which is characteristic of like devolatilization in a gas-free silicate-rich environment. So just like heating the Earth in a vacuum, that has a different like volatile loss fingerprint compared with a hot nebula gas just partially condensing. So that may be one relevant way to sort of fingerprint like a planetesimal-like stage of growth, like post-disk dissipation, small hot objects that are like just losing to vacuum.
and the other thing is like kind of NCs, non-carbonaceous chondrites and carbonaceous chondrites, and this idea that they are two separate reservoirs potentially from kind of that never joined. But if you have pebble flux all the way through your disk, it's really hard to keep those isotopic signatures potentially. So yeah, I think there are issues there to be explained. Maybe we can do it.
I was wondering, now that we have an idea about this whole process from the cloud to the planet, are we able to get a better view of what are the conditions we need to get a nice home planet?
You can solve everything for me. No, but we do, as in we can put some ideas, but there's always going to be this kind of issue of the stochasticity of it, right? Like, what was it that determined whether you grew big enough to become a gas giant or not before you at the end of your gas disk lifetime? Was that to do with just having a little bit more material there, or a lot more flux coming in, or your gas disk lifetime was shorter, or kinds of things? And those things we just don't understand, I think, why they happened.
I think if this is my perspective, but kind of from outside the field, I feel like if anything, like exoplanets, looking at exoplanets has taught us is that you can create a physical model to try and explain a given system, but it doesn't necessarily capture like a universal truth of the physics that's operating. Like, you know, we had models that could produce a solar system, right, before exoplanets came along. It turns out those models don't produce any exoplanetary systems, right? Because they're tuned in a way to replicate an architecture which turns out to not be ubiquitous. So like that question of what, yeah, like those kind of branching points where something goes differently and you don't end up with a solar system is in a way, it's like the heart of the science in all of these sub-disciplines, and you know, which we're seeing put together here by Amy.
Yeah, I would agree absolutely. And like forming a TRAPPIST system is clearly a very, very different pathway to forming Earth. But then even asking the question, well, did the TRAPPIST planets have enough volatiles or not too much volatiles? You can kind of say, well, actually, if you didn't have this outer disk that didn't have this material, maybe you could constrain it so they didn't have enough volatiles, but you don't know. Or if they accreted in a certain way from kind of pebbles coming inwards, they would have had loads of volatiles.
This has been a really fantastic conversation. Do you mind if I end it and we kind of, because I'm conscious.
I'll be around
that,
outside
yeah,
here.
last time we just placed them from their discussion series, but I wanted to, it's been a really, really fantastic discussion. I think it emphasizes that we could pick up on any one of these points in this history and have like a great kind of coffee meeting about the streaming. Like, for example, I want to know why the streaming stability, why there's any contention around it.
Come and give us a coffee meeting.
Every time I hear it discussed, it's sort of the gospel way in which we break through the, you know, the accretionary, the bouncing barrier and stuff. So yeah, we should focus on that. I want to do a small bit of advertising before thanking Amy again. So this is a 101 lecture. There are 2 more this year. Next term, we're having an arts and humanities one, the origin of life in the arts and humanities. That's being given by Andrews. That's really exciting. And just a reminder, the 101s are given by us to ourselves. So it's from our community, kind of educating each other. So Amy's kind of doing it today. Andrew's doing it next term, Andrew Davison. And then the following term, Paul Rimmer's going to be doing planetary astrochemistry. And probably perhaps convincing us why that's not an oxymoron. So that's exciting. In addition to the 101s, there's the seminar series. The main difference is that brings in external speakers. So there's 2 of those lined up. Just remind myself. So we've got Aveen van der Schick this term. Oh no, that's not. Oh yeah, that is true. Yeah,
November,
this term, November. Thank you. And then March next year, we've got Paola Caselli. So Aveen is talking about planets, what sets their composition. So kind of really a great kind of follow on from Amy's talk here. Yeah, what sets up the C/O ratio, the sulfur content of a planet. That's cool. And then Paola in March next year is talking about astrochemistry, going back to the far left of that diagram, and what the process is taking place there. So that's what's coming up. Thank you so much again to Amy. It's a fantastic kind of overview of planet formation and some of the exciting things we can talk about and work on going forward. And thanks also so much to Mej for kind of organizing things and getting us set up here. So, and thanks everyone for coming. It's great to see some new faces.